All right, engineering math. I'm out today. I've got to keep my feet raised and toe ice because I broke my pinky toe. Tell you the boring story later. Um, but this worksheet is up here on my desk. Your workbooks are over here. So make sure everyone gets the materials that they need to get started. You don't have to like cut this out and tape it in today, but if you want to, sure. But we can worry about that later. Uh, but I'm going to walk you through this. Um, we're going to, you're going to do all these examples. The examples I'm going to do here on the back. So make sure that you have a space in your workbook to take some notes, because I'm going to do different examples that are just like these, and then we're going to work through it. And this whole sheet is about parallel circuits and how they work. Okay. All right. So first, let me do our first examples are actually not about circuits, it's just about algebra and how we solve equations like this. Okay? Now, these equations are pretty basic and when it comes to what's called rational functions, things that have a fraction where x is in the bottom of the fraction in the denominator. And so, but that's, our application is going to be pretty basic and we don't have time to go like much more in depth. But the method I'm going to show you works for even as they get really, really complicated. So go ahead and please make sure, even if you can sort of figure it out in your head without using any of the complicated, or the method, it's not that complicated, please do it step by step because you're trying to build the muscle to be able to solve this even as it gets more and more complex, because not everything you can do in your head. Okay. Here we go. So here's an equation. I've got x here sitting on the bottom of the fraction. And the basic technique to solve these types of equations is to get rid of the fractions. And so to get rid of the fractions, you need to multiply by what's called the least common multiple, or least common denominator. So in this case, 6 and 3, they both go into 6, so 6 would be the least common multiple. However, if you didn't know that, you could just multiply 6 times 3, and that's 18. And even though it's not the least common multiple, it is a multiple, and it would still work. It would maybe be a little bit slower, but it would still work. So if you don't know, just multiply everything together. But then we have this x here, and we don't know what it is. So the least common multiple of this whole system includes 6, because that's the least common multiple of the numbers, and x, because I don't know what number that is, so 6 times x is the least common multiple. Okay? And then what we're going to do is we're going to multiply 6x by every fraction in here. Every fraction gets multiplied by 6x, and then as we do so, things will cancel, and then I won't have fractions anymore. So if I multiply 6x times x, I'm going to do this the slow way at first, and then you'll see in this second example, I'll do it a little more efficiently. Okay? So 6x is 6x over 1, which means when I multiply, the 6x is going to the top, and the 1 is anything multiplied by 1, so it's not going to change the bottom here. So when I do this, I'm just going to go ahead and go 6x times this right here is going to be 6x. I'm not going to simplify yet or cancel 6x or over x, because 6x went to the top, 1 didn't change the bottom. And then as I keep going, I'm going to have 6x over here, because 6x times 1 over 6. Oh, but then 6x times 2 is 12x, and then over 3. So you can see the bottoms didn't change because that's a 1 there, and the tops got multiplied by 6x. And then I can just simplify this. What's 6x divided by x? Well, that cancels, leaving just 6. What's 6x divided by 6? Well, that's just x. Okay? And then what's 12x divided by 3? That is 4x. Okay? And so if I had started this whole process with this equation, which I'm going to write more clearly over here, 6 plus x, well, can I write it more clearly? Let's try to use a different pen. 6 plus x is equal to 4x, and said, solve that. What would you do? Okay? If you are like, I don't know what I would do, I don't know how to solve that equation, then there is another Khan Academy link up on the whiteboard for those who need the help of like, I don't know how to solve these equations. I'm going to walk through this, but I'm not going to teach you how to solve all these kinds of equations. It's going to be a reminder. Okay. So what I see here is I need to combine like terms. So that means I need to subtract x from both sides. Okay. That leaves 6 on this side and 3x on that side. Well, that's 3 times x, so I got to get rid of that 3. I got to divide by 3. That'll cancel out that 3, leaving x is equal to, and then 6 divided by 3 is 2. So there's my answer. Okay. Now, when you do this, it can come out to a whole number, but it can also come out to a fraction. Either are okay. So what I want you to do right now is pause the video and try the first 3 problems, which are pretty similar to the one I just did. Okay. And then when you're ready to try this one, come back to the video and I'll walk you through this. Okay, for this one, our least common multiple, what we're going to multiply by, is 3, because I have that on the bottom of the fraction, and x minus 1. Because we don't know what x minus 1 is, we just take the whole thing. 3 times x minus 1, both of those numbers will go into. 3 goes into that because there's a 3. X minus 1 goes into that because there's an x minus 1. So I'm going to take this now and multiply it by every fraction. But this time I'm going to work through like a more streamlined thought process. So if I multiply this by this, what will cancel between these two things? What's the x minus 1? Which means what will be remaining is the 3, and 3 times 6 is 18. So let me say that again. When I multiplied these two, the x minus 1s went away, and all I had left was 3 times 6. Okay, when I multiply these ones, the 3 is going to go away, and all that's left now is x minus 1 times, and this is key, there's a minus there, times minus 4. So I'm just going to write it like this, minus 4 times x minus 1. Again, when I multiplied these two, the 3 went away, so I'm left with minus 4 times x minus 1 equals, and then when I multiply these ones, the x minus 1 cancels, so I'm just left with 1 times 3, which is 3. Okay. Now, I can just distribute this negative 4. That's how I get rid of the parentheses. So 18 minus 4 times x is minus 4x. Minus 4 times minus 1 is plus 4, is equal to 3. Okay. And now I'm just, again, going through those like algebraic steps. So 18 plus 4 is 22. So now I have 22 minus 4x. I'm combining like terms. So what I'm doing is equal to 3. Now I see that I already have x's on this side, so I want to get the numbers on the other side because I want to separate them. So I'm going to subtract 22. And the negative 4x is still there, that minus is still there, even though this disappears in front of it, because 22 minus 22 is 0. And then 3 minus 22 is negative 18. So let me move this up. Okay, so I subtracted 22 from both sides. Now I just have something with x, something with not x. I divide by negative 4, divide by negative 4, and I get x is equal to, well, the negative divided by negative is a positive, and 19 and 4 don't have any common factors, so I can't reduce. So 19 fourths. And yes, I want your answers not in decimal form, not rounded, not anything like that, but in improper form. Whenever we do pure mathematics, we write our solutions in improper form when we get to advanced levels of mathematics. Not mixed numbers, not decimals, improper form. Okay, go ahead and finish this up, and then when you're ready, I'll show you how to do these problems. Okay, I'm going to walk you through this here. This is what's called a parallel circuit. And what I want you to write in your notes is the formulas for parallel circuits. So I'm going to pull out the notes here. You can pause the video and take some notes here. I'm going to have both parallel and series circuits. Let me take my face away. Okay. Here are your notes for the day. I do want to remind you that the notes from previous days are still relevant today, but this is the notes, new notes for today. Okay. Okay. All right. Now, let me put my face back on the screen. So basically, when you have a parallel circuit, you don't add the values, you take the reciprocal of them and add them, and then when you're done, that's not the answer, that's a reciprocal of the answer. And so we're going to set up our examples that way. So here we go. Let's do this first one. So what it says is basically you go 1 over the first resistor. So in this case, the first resistor is 1.5K, or 1,500. And then you go plus 1 over the next resistor, which is 680. And if there's a third or fourth resistor, you just go 1 over the next thing, or whatever it is, capacitor or anything like that, you just continue to go, equals 1 over the total. And since the total is what we don't know in this problem, I'm just going to put x for like unknown. Okay? And now I just have this equation over here. I mean, it's not much different. So I'm going to race through this problem. Okay? This is a good example of where you don't need a least common multiple, you just need a multiple. So I'm going to multiply both sides by x, by 1,500, and by 680, because that's what's on the bottom here. I'm going to multiply it by all three. So when I multiply this first one, the 1,500 cancels, leaving 680x, because that's what's left over. When this one, the 680 cancels, leaving 1,500x. And the last one, the x cancels, leaving 1,500 times 680. At this point, there's basically two things left to do. You can add those two together and get 2180x. And then you can multiply those two together on a calculator. Let me do this quickly. 1,500 times 680, and I get 1,020,000. Okay. And then to solve this, yeah, those are big numbers, but all you got to do on a calculator is divide both sides by 2,180, because that will cancel that. It'll cancel this with that, and I'll just be left with x is equal to whatever this number is, which I divide that by 2,180, and I round it, I get 468. Okay. And so there you go. So it's setting up the same equation. Yeah, we're dealing with bigger numbers now, but that's all we got. Okay. Lastly, I'm just going to walk through this here. Okay. And to set this one up, you just do 1 over 820 plus 1 over r is equal to 1 over my total, which is 510. So here, the thing I don't know is this resistor, so I need to calculate it. But it's a similar setup, like we've done this equation, so now I'm going to multiply by 820 by r and by 510, do the same thing that we just did up here. Okay. Okay. All right, so at this point you can pause the video. You can do these ones and these ones, and this one. Help each other, and then when you're ready, I'm going to show you how to write the equation for the magnitude of total impedance. Okay, so as a reminder here in our notes, if we do series, we're just going to add them. And if we're going to do parallel, we're going to do the 1 over. Except for this one, we're going to use the green version because it says z total equals, and that's going to be easier for graphing. So here's how it works. The z total here is equal to 330 ohms. And then you just add, because it's in series, the next one, but the next one is an inductor, and so, that means we've got to use this formula. So that's 2 pi f, and yes, we're going to leave f alone here, times the inductance, which the inductance is 10 millihenries, so times 10 to the negative third, so times 10 to the negative third, and then j. And this has the magnitude, which means distance from 0, so then you just slap an absolute value at the end, and you're done. Okay? So that's how this works. So if I were to do that in parallel, I would write z total is equal to, and now I write the same thing, but I write 1 over 330 plus 1 over 2 pi f times 10 to the negative third j, all underneath that fraction. And then the formula says, and again, I'm referencing our notes here that I had you take, this note right here, to the negative 1 power is what it says. And then it's the magnitude, so When I'm done, I take that whole formula and I put absolute value. Okay? And this is how you do that. So if you're doing parallel, you do 1 over and 1 over. If you have a capacitor that it is a fraction, the formula for a capacitor is a fraction, so you will have 1 over a whole fraction, and that's okay. You'll have 1 over that, 1 over that whole fraction when it comes to a capacitor. And so, yeah, you'll work through that. We'll spend most of our time on Friday working through this.